Hey everyone, and welcome back. Today, we're diving into one of the most fundamental ways an AI can actually reason. It's a process called forward chaining, and honestly, it's what turns a machine from just a number cruncher into something that can connect the dots, moving from a pile of facts to a logical conclusion.
I mean, it all really starts with this massive question, right? We know computers can blaze through data at unbelievable speeds, but how in the world do they make that leap from just having raw information to reaching an actual logical conclusion? How do they connect those dots?
Well, the answer lies in this powerful little process called inference. And we're not just talking about calculating things here. This is all about deriving brand new knowledge from what's already known. You could say it's the engine of AI reasoning.
And this right here is the key difference between just knowing stuff and actually understanding it. Inference is what lets an AI get the implicit meaning, to read between the lines. It connects the rules it knows to new pieces of evidence to figure out something that was never spelled out for it.
But here's the thing. For an AI to tackle really complex problems, it needs a way to reason that's both super powerful and flexible. A simple if this, then that just doesn't cut it when you're trying to make sense of the real world.
So on one hand, you've got what's called propositional inference. It's pretty straightforward, dealing with simple true or false statements, like, it is raining. But that's kind of limited. For the heavy lifting, we need first-order inference. It's way more abstract, and it lets us create these general universal rules about the world, like, for any person X, if that person goes out in the rain, they will get wet. See the difference?
Okay, so to pull off this more powerful kind of reasoning, an AI needs a formal language, a really structured way to represent all its knowledge. And that language is first-order logic. Think of it as the grammar that a technique like forward chaining uses to think. In this language really boils down to three key building blocks. You've got variables like the letter X, which are basically just placeholders for things. You have quantifiers like for all or there exists, which tell us the scope. And then you have predicates, which are just statements about those things that can be true or false, like is a human.
All right, so that's the theory. But how do all these parts actually work together to create knowledge? Let's walk through a super classic example to see how it all clicks into place.
First up, we give our AI a general rule, something for its knowledge base. In first-order logic, this would sound something like, for all X, if X is a human, then X is mortal. This is a universal truth that we're handing to the AI. Next, we drop in a specific, known fact. We tell it that a particular individual, Socrates, fits into that human category.
And boom, this is where the magic happens. By combining that general rule with the specific fact, the AI derives a brand new piece of information it was never told directly. Socrates is mortal. So the question is, how does an AI do this step all by itself?
And that, my friends, brings us to our main event, forward chaining. It's one of the main strategies an AI uses to pull off this kind of logical deduction. And honestly, the best way to picture it is to imagine the AI as a detective who's just shown up to a crime scene.
Now, this detective doesn't start with the suspect in mind and try to work backward. Nope. This detective starts with the clues, all the known facts, and just sees where the evidence leads them, one step at a time.
So the most important thing to get here is that forward chaining is what we call a data-driven approach. It looks at the facts it has, scans its rulebook for anything that matches, and then bam, it generates new facts. It literally chains its logic forward, from the evidence it has to a conclusion. So here's the detective's playbook. First, it looks at all the known facts. Those are the clues. Then, it searches for a rule where the if part perfectly matches a fact it already knows. When it finds a match, that rule fires, and the then part of the rule becomes a brand new fact, a fresh lead in the case. The AI adds this new fact to its list of clues and just keeps repeating the whole process, creating this awesome logical chain reaction.
Let's make this super concrete with a quick example from an expert system. Let's say the knowledge base knows two things. The patient has a fever and the patient has a cough. The AI finds a rule that says if a patient has a fever and a cough, then they might have the flu. Well, since both of those if conditions are true, the rule fires and a new fact gets added to the knowledge base. The patient might have the flu. Simple as that.
So, okay, it's a detective, but why is this bottom-up reasoning process so important? Where does this stuff actually show up in the real world?
Well, it's the backbone of so many expert systems. Think about a medical diagnosis program that takes in your symptoms, the facts, and works its way toward a potential illness. It's also huge in real-time monitoring,
like a network security system that sees weird data packets, the facts, and applies its rules to flag a possible cyber attack.
So if you take one thing away from all this, it should be this. Forward chaining lets an AI be really reactive and, opportunistic. It just works with whatever data it has right now to see what conclusions it can draw, building up its understanding of a situation from the ground up.
Which, of course, leaves us with a pretty fascinating question to chew on. If our AI detective is this good at reasoning forward from the clues to a conclusion, what would happen if it started with a hypothesis, a potential goal, and tried to reason backward to see if the evidence even supported it? Well, we'll just leave that one for you to think about.